Hi, my name is Pat Randall. I'm the West Coast Sales Manager and Technical Assistant, and Bob Kelly supports the East Coast. Either of us can answer your questions regarding international applications. East of the Mississippi, Bob Kelly is the local source of information and help. Combined, we have over 50 years' experience in design and implementation of in situ and ex situ remediation systems. Today, I want to discuss how we design remediation systems using zero valent iron, ZVI. There are many benefits to ZVI over other methods. It is a abiotic degradation, and I will go into that more detail later. There are not intermediate products such as DCE and vinyl chloride formed. There is not a need to precondition the aquifer to provide activation. pH effects are minimal, and it works over a wide range of pH. There is not heat produced, and the most important is ZVI has an active life of over 10 years. ZVI is matched to project requirements, typically by particle size. Ferox PRB has an average particle size of 325 microns, about the same as construction sand, and is the most economical and has the longevity over 10 years. Ferox Flow has a particle size of 125 microns on average and is easily injected by direct push and other methods. Ferox Target has an average particle of 40 microns and is the most reactive of all three. This slide shows some photographs of the Ferox ZVI products. The next two charts show some of the compounds which are treatable with ZVI. These can also be seen on our website. Bob has recently posted an article discussing treatable compounds. In addition to many chlorinated solvents, ZVI is an effective treatment for removal of soluble metals, sulfates, nitrates, phosphates, and arsenic. One big advantage of ZVI over a biological process is the abiotic pathway does not form any DCE or vinyl chloride. Any of the chlorinated ethenes can enter the abiotic pathway and bypass DCE and vinyl chloride. In order to design ZVI applications, we must first look at the first order degradation rate model. This model shows the final concentration as a function of the initial concentration, a degradation rate constant, how quickly the ZVI reacts, and time. Time the contaminant is exposed to the ZVI. The reactivity is based on the particle size, with PRB being the lowest in reactivity and target the highest. By charting the change in concentration versus time using data from batch or column tests, we can do a simple linear regression fit, and the slope is the rate constant. In this case, K observed is 0.088. This is the observed rate constant for the concentration of contaminant, the amount of iron, and the time exposed. To complete our model, we want to derive a K mass by adjusting K observed for the volume of water treated in the time interval and the amount of ZVI used in the treatment. We can now make predictions for other conditions. KSA is a reaction rate based on the surface area. This is a direct relationship. However, we buy ZVI by the pound and not by the surface area, so it's not a practical term to work with. We can get K observed and K mass by performing a batch test. A fixed volume water is treated by a fixed mass of ZVI. Samples removed from a bottle are analyzed over time and provide the data for our regression to get K observed. And the volume water and mass of Z of I will be used to adjust K observed to get K mass. That's the iron and the water, and we can collect samples. A column test yields much of the same data. However, more site-specific characteristics can be used, such as flow rate, site soil, and site water. Samples collected from the ports at various intervals represent different times exposed to the ZVI. Using our test data, we can estimate a K-mass for the model. By making some substitutions in our simple first-order model, we can use site conditions to determine how much ZVI will be required for the project. We will now look at a barrier placed in front of the plume. Many applications are barriers due to the long life of ZVI. This allows for containment of the plumes and prevention of off-site migration during the process of assessing the on-site impacts and developing source and remediation methods. This slide shows the design parameters needed for the model, namely the front of the plume dimensions, concentration of contaminants, and groundwater flow rate. By putting these parameters into a model, the estimate of the amount of ZVI required for the site conditions can easily be estimated. Bob and I can help in this process. We also screen by a secondary condition. Some conditions can result in very low ZVI requirements, and there is not adequate ZVI to ensure contact as a contaminant flow through the barrier. The frontal area percent prevents the contaminant from passing through the barrier without first encountering ZVI. The source or plume area can be treated by typical low and high pressure injection methods. ZVI, typically target and flow, are mixed into a water slurry and injected into the aquifer. The model has some slight modifications to allow estimate of the quantity of ZVI required. A secondary test of the ratio of ZVI to soil mass is used to prevent the low flow, low concentration estimation issue. The first model only considers how much ZVI is needed to provide adequate reaction to the contaminants. To ensure longevity of the iron, we need to include other demands. There are major anions in the water which can make up most of the ZVI consumption. The model looks at additional demands over time to ensure enough ZVI to last the life of the project, in this case 5 years. In situ groundwater treatment, treatment of mined waters, pretreatment of drinking water, and nitrate and phosphate removal from ponds and lakes are some of the most common use cases for zero valent iron. Thank you for watching our video. If I can be of any help, please call or email anytime. You may also look on our website, hepier.com. It contains a lot of information about zero-valent iron and a lot of other remediation chemicals. Bob Kelly is your resource east of the Mississippi River. He represents the entire eastern seaboard. Combined, Bob and I have over 50 years experience in design and implementation of in situ and ex situ remediation systems. Please call or email anytime if you need assistance.